Welcome back. We're today broadcasting from this beautiful mathematical storeroom. You can possibly hear the servers whirring away behind me there. Hopefully, that's not going to cause too much of an audio problem. But yeah, so today I'm going to take you through the week 2 exam problems that were due on Monday. And I'll again try and make a video like this every week, even if I can't get through all of the exercises. So, starting things out, we have here this first exam question here, which is a classic addition of ordinates type problem. So, what we have is we have a blue graph and we have a red graph. And I'm going to create a green graph that represents the addition of these two graphs. So, I want to represent what does it look like when I have f of x plus g of x, and I'm going to call the result like whatever I want to call it. I could call it h of x. Don't really need to call it anything. But what does the addition of these two graphs look like? So what we're actually doing here is we're going to take the output, so the y value of each of these functions, and we're going to add them to each other, and we want to have a think about what the result will look like. First thing you need to realize is that when we have an addition of ordinates like this, the output will only be defined if both of the functions are defined for that input. So what I mean is, if you have a look at the first red graph here, you can see that there is an asymptote at x equals 0. So therefore, if we think about the outputs of f of x, it will never be defined when x is equal to 0. So for example, if this red graph was y equals 1 of x, then you can imagine if x equals 0, we're not going to get an output down here. So if we have, for example, y equals 1 over x, and this looks like maybe x cubed, if we have y equals 1 over x plus x cubed, this is going to be equal to, if we sub in 0, we're going to get 1 over 0 plus 0 cubed. This is undefined. So the point being, when we add or combine functions in different ways, the two functions that we're combining need to both be defined. So that's a long way of saying that this graph will not be able to be sketched along this asymptote x equals 0. Okay, but what about the rest of it? So what we can do now is we can consider key points. And addition of ordinates basically means go point by point, consider what the output will look like when we add the two functions together, and also have a look at the endpoints. So as we approach the asymptote, as we approach infinity, as we approach negative infinity. So starting things out, let's just consider this point right here. So at this point, let's suppose that's like maybe 1. I don't know what it is. The red graph is equal to 1 at that point. So the y value of the red graph is 1. The y value of the blue graph is also 1. So if we go 1 plus 1, that brings us to 2. So it's going to be about twice the distance away from the x-axis here. And that's where we end up. Okay, so that there is, that's our graph of f of x plus g of x. Let's take another point. Let's say, for example, this point here. So I'm going to consider maybe like along this little line here, let's say. So I want to add the red graph to the blue graph. So we're going to have this blue graph plus this red graph. That's going to put us a little bit above where the blue graph is. So we're going to put it like that distance above where the blue graph is. Let's choose another point. Maybe we're going to choose this one right here. So we can see that's going to be this blue graph plus this bit of the red graph. Now you can see that's a pretty small number. It's a little bit smaller than this number here, so we're actually going to be a little bit closer to the blue graph. And in fact, as we continue to do this, we're going to be adding a really large number to an increasingly small number. And what that will look like is we're going to be getting ever closer. Try and draw this as carefully as possible. We're trying to get ever closer to that blue graph. So we start further away, and as we go along, we're getting closer and closer. So that blue graph becomes sort of an asymptote for our addition, f of x plus g of x. Let's consider something else. What if we move in this direction? So let's choose, for example, adding points along this line over here. Try and make this a vertical line. There we go. So we have here, we have what appears to be a very small number, pretty much 0, plus a number there that is clearly quite large. So if we have that number there, plus this number here, we're going to effectively just be at that exact point. Not quite, but again, it's going to be very close because we still have a number here that's not quite 0, but we're going to be getting very close to 0. In fact, I think it'll get closer it'll get closer to 0 faster than on the other side. So we're going to, again, have like an asymptotic sort of behavior getting progressively closer on that side. So we kind of have almost like a parabolic sort of shape, but it's not a parabola. It's an addition of these two graphs. And in fact, this one's getting closer much faster, and this one's going to continue off way over here. It's going to keep going forever. This one's just going to approach 0. So this one has an asymptote at 0. This one has an asymptote along that line of the blue curve there. All right, let's look at the in the negative direction. Same thing. If we look at this point here, we have that negative number, so -1 maybe, plus -1 brings us to -2. And then if we look over here, we have a very large small number, so a very small negative number. It's got a large magnitude, plus a small negative number over here. And that's going to put us somewhere above this blue curve if we add those 2 points together. And as we move further down this curve, we have a very small number plus a very large negative number. So it's going to be the exact same sort of thing that we saw up here. We're going to see this line taking on asymptotic behavior that is approaching the blue line but never quite reaching it. And the same thing goes for over here. We have an asymptote that is approaching that red line, and like I mentioned before, it's going to get there pretty quickly. It's going to look something like that. That looks about right. So very small negative number, basically 0, plus something that's getting pretty big. We're going to get a curve that looks something like that. All right, let's try it again. So we have this one over here. Go step by step. So step 1, note where it's not going to be defined. So that's going to be along this curve, right down the middle, along that, that asymptote of x equals 0. So x will never equal 0 for this curve. Then let's consider our points. So consider first the point where the two graphs are the same as each other. It's these 2 points right here. That plus itself is going to put us here. All right, so that looks like about 1. So 1 plus 1 equals 2. We end up here. Okay, now let's consider the endpoint behaviors. As we move in this direction, we have an increasingly large number plus an increasingly small number. So we're going to get really close. We're going to get really close to that curve, but we're never going to quite reach it. Same thing on this side. We're going to get really close to that curve, but we're never going to reach it. And it's going to start out being further away, and it's going to get progressively closer. It's hard to draw it with this mouse pad, but hopefully you can see what I mean. Okay, there we go. And then same thing on the other side. It's going to get really close, but it's never going to reach it. And make sure it doesn't cross over the red line. Why can't it cross over the red line? Because we have a number here, that red number, wherever it might be, like maybe here. So it's about 5 at that point. And we look along that line at that x value. What is the blue value equal to? Well, it's equal to a number that is not 0. And it's not possible for us to have a positive number plus a positive number and end up smaller than the first positive number. How does that make any sense? So we can't cross that line, as we can see here. So that's roughly what the shape will look like. And you can put arrows on the ends. It's important that you do this just to indicate that it's going to keep going like that. So never just end it like this. We need to put arrows there to say that it will continue. And I think in VCAR, they might actually take off marks for that. So yeah, this goes for any graph. Same, honestly, they should have included arrows here. We should have had arrow there to say that this curve continues like that, because otherwise we might think that the domain is restricted and just cuts off right there. Anyway, that aside, let's move on to the second question. So question 2, we are required to start with this little function here. So we've been given a function in function notation. We've called the function f. The function has a domain of r excluding 1 over 3. Why is that? Because if we look at the rule for the function, if we put in 1 over 3 into that function, we're going to get 3 times a third. So that's 1 minus 1 down the bottom here. So that's 1 divided by 0. So that's a problem. So this can't be equal to 0 because then this is undefined. So therefore we have to exclude 1 over 3. So that's just understanding what this says. Now here it says, find the rule for f inverse. So f inverse, this is, if we recall, the inverse of a function. And the inverse of a function basically means if this is the that's the y-axis, and that's the x-axis. And let's say we have some graph that looks like that, or let's just put in a classic parabola maybe. So we just have a parabola there. So hard to draw with this. There we go. We've got a little parabola there. What the inverse of this function would look like. So let's suppose that blue function is f of x. The inverse of this function is where we basically swap the x and the y-axis. So this is going to become the y-axis of my f my f inverse function, so it's going to be the exact same as this blue graph, just with this as the y graph. So just imagine if we like tilt your head, and it's going to kind of go like that. It's going to kind of go like that. You can see it's the same shape, just being tilted to the side. Another way of thinking about it is that we have this line y equals x, right? So the curve y equals x, and I'll try and draw this properly because it should be passing through like this. So it's going to go right down the middle of those two curves, this line of y equals x, and the blue graph has been reflected in this line of y equals x, and that's generated the green graph over there. These are a couple of ways of thinking about the inverse function. That's just a quick refresher on what the inverse function actually means. So let's move on and consider the rules over here. So firstly, we need to find the rule for f inverse. How do we do that? Well, the first thing we do is we replace what is the y in this equation. So the equation is y equals 1 over 3x minus 1. We're going to replace the y with x, replace the x with y, and then rearrange the equation to make y the subject. And that's going to be the rule for the inverse function. Okay, so let's give that a shot. I'm just going to write this equation in blue down here. Let's go for it. So A, we have, okay, so y is going to become x. So we have x is equal to 1 over 3y minus 1. Okay, there it is. So now we need to rearrange this to make y the subject. First thing we might want to do, both sides, multiply them both by 3y minus x. So we're going to get 3y minus x times x is equal to 1. So I've just times this by 3y minus x. So 3y minus 1 divided by 3 minus 1 is equal to 1. And then we can divide both sides by x here. So we get 3y minus 1 is equal to 1 over x. And then we can plus 1 to both sides. So 3y is equal to 1 over x plus 1. And then divide both sides by 3. Y is equal to 1 over 3x plus 1 over 3. Okay, so there is our equation for y. And if I put this into function notation, which you always should do, we're going to give the function a name, then we're going to specify the domain. The domain is all of the real numbers excluding 0. Why is it excluding 0? Because if I put 0 down the bottom here, then I'm going to get 1 over 0, which is undefined. So that is not allowed. The codomain is always R. Don't have to worry about that. F inverse of x is equal to 1 over 3x plus 1 over 3. So that is the rule listed in function notation. Okay, let us consider now part B. So part B says state the domain of f inverse. Well, I've actually already done that. That's just this. So the domain is, and remember this is a restriction on the x values, all of the x's, so x is an element of all the real numbers excluding 0. We could also write this as x is greater than or equal to, well, I guess the problem is just can't be 0, so we can have x from negative infinity up to 0 union with, in fact, a better way to write this using interval notation would be like this. We could say negative infinity up to 0 union with 0 up to positive infinity. And then I guess we could say x is an element of that. So both of these are perfectly valid ways of representing the domain. All right, now the harder part of this question is part C. So this is probably the part that you were confused about. So part C, it's a bit wordy. So it says the graph of f is translated C units horizontally and D units vertically, where C and D are elements of R. Let G be the function corresponding to the translated graph. Find the values of C and D, given that G is equal to F inverse. Okay, so let's just chuck that in straight away. So we know G of X is equal to F inverse. So that means G of X is equal to 3x, 1 over 3x plus 1 over 3, because that's what we've defined F inverse as. Now let's try and unpack what all this translation stuff is talking about here. So first up, it says F is translated C units horizontally. So let me just use some notation that the specialist students might be familiar with, but everyone else will really benefit from thinking about transformations in this way. So let me just get that back up. I seem to have lost my ability to change colors, which is kind of annoying, which is fine. Should be able to do with this. So let's say we have our x value. We're going to call this x prime, which is to say this is the image of x. after a transformation is applied. So what this means, the graph is translated c units horizontally. That just means that what was our original x is being shifted c units, and this results in our new x. So this is like the new x, this is the old x. Okay, that's what the prime means, the new one. So that means what we have here, so the graph of f of x, that's equal to 1 over 3y minus 1, right? 1 over 3x minus 1 from the original question just up there. So what's happening here is we're going to take the x from that expression and we want to replace it. We want to write it with the new x. So how can we do that? Well, we can take that x and we can rearrange this formula here. We can write this as the old x is equal to the new x minus c. So let me just substitute that into here. So I want to write this in terms of the new x. So the new x, I guess f in terms of the new x, is equal to 1 over 3 of x minus 1 minus 1. So that's why it's when you see function notation written like this, the x minus 1 means a translation in the positive direction. So I've just replaced the x with the x minus 1 there. Okay, same sort of idea here. We have the y. So the y new, so the new y is equal to the old y plus d. Okay, so if I rearrange that, we could write this as the old y is equal to the new y minus d. Now here's the old y over here. Yeah, because y is equal to f of x. I'm going to replace that. So let me just do this over here. Replace that with y, the new y. Remember, this is the new y minus d. And if I want to rearrange this to make y the subject, I just plus d to both sides, and that's why we end up with plus d in our expression. So if I write this, just combining all this, you don't really need to know that background, but you can just say that the function after these transformations is applied is going to be equal to 1 over 3 of x minus 1 plus b. And again, if you just want to memorize this and not worry about it too much, we just remember that when x is being translated in a positive direction, we're going to have x minus 1 down the bottom here, and y, for some reason, it's a plus at the end of the equation. So that difference there can be a bit weird, but we've seen this pattern before. Just remember, we've seen this pattern before. Okay, so what we're saying is that this thing here, after these transformations, so I guess it's not really f of x, is it? It's kind of the new equation. That is actually the exact same thing as g of x. So therefore, we have that g of x is equal to, because that's what we've been told in the question, g is the function corresponding to the translated graph, and it's also equal to the inverse. So g of x is equal to the inverse, 1 over 3x plus 1 over 3, and it's also equal to this translated graph. So that means it's equal to, so that should be a c, 1 over 3 of x minus c minus 1 plus d, right? So what we want to do is we want to figure out what are the d and c values, and you can kind of actually just look at this and see what the d and c values are going to be. But for example, if you look at d is simply going to be equal to 1/3. See, you've got the 1 over 3x bit here, and then you have this translation vertically factor over here of plus 1/3, so d must be equal to 1/3. Okay, to find c might be a little bit harder. We can just look at the denominator of this fraction and the denominator of this fraction over here, and go ahead and make them equal to each other. So we found d was equal to 1/3. Let's have a look at this bottom part. We have 3x is equal to 3x minus c minus 1, right? So that denominator is equal to this denominator. Okay, so first thing we might want to do is expand this bracket, 3x minus 3c minus 1. And then let's subtract 3x from both sides. So that just becomes 0 is equal to negative 3c minus 1. Let's plus 3c to both sides. 3c is equal to negative 1. And therefore, we can see if we divide both sides by 3, c is equal to negative 1/3. And now we found d was equal to 1/3, c was equal to negative 1/3. That should work. There we go. All right, so now we've successfully answered that question. Okay, moving on to the final question here. First thing we have to do is solve an equation. Second thing we have to do is plot a function. So let's start out with the first part of the question, which is solve 2 cosine x, and then we have plus 1 is equal to 0 over the domain of 0 to 2 pi. Okay, so this is our classic trigonometric sort of question. And the very first thing that we want to do here is rearrange this to make the cos, sine, tan bit by itself on one side of the equal sign. So if you do that, we'll minus 1 from both sides, then we'll divide both sides by 2. We get cos x is equal to negative 1 over 2. Okay, second thing you want to do is look at that and then have a think about how would we solve this? So the first thing you would do is maybe just see if you can find the base angle, which is to say, in the first quadrant, if we ignore the negative sign, let's see if we can work out a question like this. So this is sort of an aside, I guess, an aside over here. If we just had cos of x is equal to a half, ignoring the negative sign, what would x be equal to if we just looked in the first quadrant? Well, what we might do is look at our triangles that we are familiar with, because it's always going to be related to those two triangles. We have the first one, which looks like this. It's like an equilateral triangle with side length 2 that's being cut in half. So this length here is 1. If it's equilateral, that means that this is 60 degrees, or pi on 3 radians, and this one up here is pi on 6 radians. And if we use Pythagoras' theorem, this side length here is going to be root 3. So if we look at that special right triangle over there, we can see the 1 and the 2 are over here. So we're dealing with cos, so that must be adjacent over hypotenuse. So soc, cot, toa, cos, adjacent over hypotenuse. Therefore, the x is equal to pi over 3. So we would have an answer of pi over 3 in the first quadrant. Okay, so now let's consider our unit circle and look back over here to try and answer the question that we're actually interested in. So let's suppose pi over 3 is like there on a unit circle. Now, what we are interested in is when, so remember, cosine is the x-coordinate of a point on the unit circle. When is cosine equal to negative 1/3? So we know that it's equal to positive 1/3 right here. What points are symmetrical to that? Well, if we consider over here the points which would be, cosine, so this must be positive 1/2. This would be negative 1/2 over here. That's that point there on the x-axis is a half. This point over here is negative 1/2. What angles give us the exact same, give us a negative half for the x-coordinate, that is to say the cosine? We would look here, and we could look here. That angle and that angle are both going to give us negative 1/2 as the x-coordinate of those points. So a point that exists here and a point that exists here is going to have an x-coordinate of negative 1/2, right? That's how coordinates work. Okay, so what we can do is, and also we could arrive at the same conclusion if we remember like our rules. So cast, where's cos negative? It's negative in this quadrant and this quadrant, because they're the only two that, so A means all, C means cos is positive there, sine and tan mean they're the only ones that are positive there, so cos must be negative in those quadrants. So there's the two ways of thinking about it. Regardless, we should end up with the fact that cosine will be negative 1 over here, and those are going to give us the solutions of, so this one here is going to be pi minus pi over 3. So pi minus pi over 3, and pi plus pi over 3. That's this solution over here. So we've gone pi, which is 180 degrees, plus pi on 3. It's the same angle. All these angles are the same as each other. Okay. And if we simplify those down to write them in standard sort of form over one denominator, we could write them as 2 pi over 3 and 4 pi over 3. So that's our answer. And those are all of the answers within the first rotation around that first rotation around the unit circle. They're the only 2 points where the x-coordinate of the point rotating around the unit circle will be equal to negative 1/2, right? It's only going to happen twice. It's going to happen when it's here, this part on the circle. It's going to happen down here, that part of the circle. All right, so those are our two solutions. Let's move on. So second part. So we need to sketch this. So first up, we've got our graph here. We want to sketch that function, this one here. So first up, let's use the fact that we have those two solutions. Now, what exactly are those two solutions? That's when y is equal to 0. Those are our x-intercepts. So we found now that our x-intercepts occur at 2 pi over 3 and 4 pi over 3. Those are our two x-intercepts. Okay, next things we might want to work out when looking at this function are the following. We might want to work out where is the mean position. So that is also known as the equilibrium, which is just like where is this curve oscillating about. So we have this translation factor up of +1. That is going to be our mean position. So we can put in a dotted line where the mean position is going to be. We only have to go up to 2 pi because that's where our thing cuts off. So the mean position is at 1. What about the amplitude? So the amplitude is to say how high up and down will the graph oscillate. So we can see here there's a 2 out the front of the cosine. So anything that goes into that cosine is going to be somewhere between -1 and 1, because those are the limits of sine, cos, and tan. They're a point going around the unit circle, so it can be up the top, so 1, or it could be down the bottom, -1. So the amplitude is going to be that number times 2. So at most it's going to be 1, at least it's going to be -1. We're going to have 1, sorry, we're going to have +2 or -2 plus 1. So if we think about +2 plus 1, that brings us to 3. And if we have -2 plus 1, that's going to put us to -1, so down here. So that's going to be our maximum point. That's going to be our minimum point. All right, final question. What is the period of this function? So the period is going to be equal to 2 times pi divided by the coefficient of x. The coefficient of x is just 1 here, so the period is 2 pi. Okay, and now we're just going to try and put it all together. Another very useful question to ask is when will this curve pass through that equilibrium point? So that is going to occur when cosine is equal to 0. So let's just consider the case where we have maybe f of, let's consider, well, when is cosine of x equal to 0? When is that? Well, that happens point around a unit circle, so that happens, so x coordinate is 1 here, then the x coordinate is 0 there, so that's at 90 degrees, and it also happens at 3 pi on 2, so 270 degrees. So x is equal to 0 at when x is equal to pi on 2 and 3 pi on 2. Okay, so those are our two points where cos of x is equal to 0, then we're going to have 0 times 2 plus 1. So we're just going to end up at 1 on this equilibrium line. So where's pi on 2? Well, this is pi. So pi on 2 is going to be halfway between 0 and pi. So it's going to be about there. Same over here. So halfway between pi and 2 pi, that's going to put us about here. Okay, and then we've kind of got our skeleton for what this graph might look like. We might ask ourselves, when will this thing be at a negative or at a minimum? So when will the minimum occur? The minimum will occur when cosine x is equal to -1. Because if cosine x is equal to -1, we're going to get -1 times 2, so -2 plus 1. So that is going to be when cosine x is equal to -1, and that's going to happen when x is equal to pi. If we consider a point on the unit circle, the x coordinate of that point is negative when we're over here. It's -1 when we're over here, right? So that's the x-axis. This is the negative x direction. Okay, and it's also going to be +1 at the start. So when the angle is equal to 0, or when the angle is equal to 2 pi after one full rotation. So we're going to have maximums here and here, or maxima here and here, and we're going to have a minimum here. And we can now see roughly what the shape is going to look like. It's very important that you get the shape right, though. So these curves, they kind of have this wave-like shape. They go down like this. Now, don't just draw like a parabola, right? It goes down like this. Then when it reaches the equilibrium line, it changes concavity. It's almost like a stationary point of inflection. It flips the direction. So up until now, it was curving like that. Now it's curving like this. It goes down, it reaches its minimum. So something like that. Reaches its minimum. Then it goes back up. Gets to this point here and it changes concavity again. So now it's curving that way. And there we have a nice little cosine curve. Chuck in a couple of solid dots on either of the two endpoints just to indicate that we're including the endpoints, and then label each of the key coordinates. So this is 2 pi 3, this is 0, 3, this here is -1, that should be pi -1. And then we have our x-intercepts, which are 4 pi on 3, 0, and 2 pi on 3, 0. We should also label the points where the curve intersects the mean position, so I'd recommend us doing that as well, just in case that's something that VCAR's looking for on this question on the exam. So that's pi on 2, 1, and this point here was 3 pi on 2, 1. There we go. Covered all our bases. Should have everything that the examiner is looking for listed on there. Okay, that's all for today's video. Hopefully that wasn't too long, and I will see you guys in class. Have a good day.